Hello, my name is Michael Fernandez. I am currently enrolled in Dr. Ross's Chemistry 102 course at East Los Angeles College, and today I will be giving a presentation on the connections between entropy S, equilibrium constant pressure, equilibrium constant concentration, equilibrium constant, delta G, otherwise known as Gibbs free energy, and Gibbs free energy at standard conditions. So first we're going to start off with the second law of thermodynamics, which states that entropy is greater than zero. This also means that entropy is always increasing. Moving on, we'll see that entropy can be defined as S equals K, the Boltzmann constant, ln of W. W representing your ignorance. K, the Boltzmann constant, being the gas constant over Avogadro's number. S can also be entropy, can also be stated as chaos or all the possible rearrangements in a system. And we can see that further moving on, we'll see that S is related to another equation that states that the change of entropy in universe is equal to the change in entropy of surroundings plus the change in entropy of the system. And we'll see that delta S of surrounding can be further defined as delta S of surrounding equal to negative delta H over T. Now, something interesting to note here is that if delta H is positive, causing delta S of surrounding to be negative, then negative plus means that this delta S of system has to be increasing, meaning so that the second law of thermodynamics will still be true. So then we move on, and we'll see that Gibbs free energy equals delta H minus T delta S. And here we'll see our first major connection of delta G and entropy right there. And this is at non-standard conditions, and further moving on, we'll see that delta G equals delta G standard, delta G at standard conditions plus the the gas constant times temperature, that's ln Q. Q being the reaction quotient. This is at non-standard conditions, and if we substitute delta G for 0, we'll see that delta G standard at standard conditions equals negative RT ln K, K being the equilibrium constant. And we'll see that here we have relationship between delta G and delta G at standard conditions, and here we'll see delta G standard conditions related to K. So we'll further move down onto these graphs. These graphs represent the Boltzmann style decay, with A represented by this line and B represented by this line. Both of these two graphs represent an endothermic reaction, and here we'll see this is an energy dominated system and this is an entropy dominated system. So we'll see here that the energy levels represented by these lines are equally abundant in both A and B. So therefore, reactants are going to be favored in an energy dominated system because A is more accessible, as you see more area of these lines being under this Boltzmann style decay graph. But in an entropy dominated system, we'll see that B has many more levels, making it more accessible, therefore favoring products being B. And we'll further see a connection between Q and K actually to this graph with G standard and K and Q. So we'll see here that Q represents the reaction quotient, and K represented here is when the reaction reaches equilibrium. And we'll see that when a graph is not at equilibrium, or when a reaction is not at equilibrium, will actually be along this curve. And as it proceeds to equilibrium, the reaction quotient will proceed to finally equaling K at equilibrium. And we'll see that this also represents a reactant-favored reaction, because we'll see that this equilibrium point is further left than right. Another interesting thing to note here is that delta G is equal to 0 at equilibrium, which links delta G and K here. And it's also important to note that K is less than 1 in reactant-favored equilibrium. And if we move on further over here, we'll see the opposite is true. We'll see that K is further to the right than to the left, meaning that products are going to be favored. And we're going to see that Q is going to end up further towards the product side than the reactant side. And in this case, K is going to be greater than 1. And still true that delta G is going to equal to 0 at equilibrium. And we can move back over here towards K, and we'll see that this K is actually Kc. This Kc is here relating Kc and K forward. Now Kc is representing reactions that reach equilibrium, but this K constant is actually different from this K, because this K only represents one direction, as we see here. This being the connection between equilibrium and kinetics. This K represented in this Kc equation. And we'll see that Kc actually relates directly to Kp, equilibrium constant pressure, through this equation that states that Kp equals Kc times RT delta N being the change in moles. And we should go back here to highlight the fact that at equilibrium, the rate forward is going to equal the K reverse, therefore equaling Kc. And we're going to go back to this equation that states that rate equals K, A to the X, B to the Y. Now this is important because this tells us something about the characteristics of certain orders of reactions. And we'll see this is determined by X and Y. Now X plus Y equals order, and each of these orders have their own specific characteristics. So the three main orders that we talk about in Chemistry 102 are 0th order, 1st order, and 2nd order. And we'll see that 0 order equals final concentration equal to initial concentration minus Kt. First being the ln of the final concentration equal to the ln of the initial concentration minus Kt. And finally, the 2nd order being 1 over the final concentration equal to 1 over the initial concentration plus Kt. And it's also important to notice that for 0th and 2nd order reactions, our reactions are going to be affected by initial concentration, A naught, A naught. But in 1st order reactions, we're not going to be affected by initial concentration. We'll see that if this ln moves to the other side, we'll end up with a resultant fraction. And because of that, initial concentration will not be affecting the rate and the ultimate time that it takes for reactions to go to completion. And we can move further back down here towards the Arrhenius equation that states something very important about K values. We'll see that K at different temperatures are different values. So a K that might, for instance, if we go back here, might be here at a certain temperature. If the temperature is raised, it may shift this way. It shifts the whole graph this way, and shifts the whole graph this way if the temperature gets lowered. So we'll see that the Arrhenius equation can be used to solve for another K if given one K and then the temperature at a different temperature. And this also includes the activation energy of the reaction. And activation energy can actually be affected by catalysts. Catalysts lower the activation energy and cause the rate to increase. So how they work is through the Heisenberg uncertainty principle, which states that the change of position times the change of momentum is less than or equal to the Heisenberg constant over 2. And if this is further manipulated, we'll see that ultimately E can be substituted for EA, so that EA activation energy is proportional to 1 over time. So what this tells us is that as we know time, E tends to 0, meaning E tends to 0, otherwise known as EA, meaning activation energy will tend to 0 as we know time. And we'll further see another link between K and delta S to this other equation, which states that ln K equals delta H over R times 1 over T plus entropy at standard conditions over R. And we'll say there's a link between K and S right here. And we'll see that through all of these equations, we can all follow the roots through this Gibbs free energy equation back to the second law of thermodynamics, stating that entropy is always increasing. It's also important to notice that as reactions go towards equilibrium, they often release heat, which in turn increases the delta S of universe, which is the entropy of the universe. And with that realization, I conclude this presentation. Thank you for watching.